So let's see if we can solve for these questions that they have in the tutorial exercises. And I'm hoping the main the bigger I don't want to say bigger issue is not the concept, but just inputting whatever they're asking for. And it gets a little tricky sometimes, because in your head you're probably thinking of something maybe a step or two ahead, and then but the computer wants you to do something else. So let's walk through this and see what happens. So it says here we want to find out if this particular limit exists. To examine this, we are going to approach 0, 0 along the x-axis. So on this path, all the points, if it's on the x-axis, what can you say about? Can you describe the x-axis as a function? Can you describe the x-axis as a relation? What? Y equals 0. So the x-axis is exactly y is equal to 0. When you graph y is equal to 0, you're going to graph the x-axis. So what we're going to do here is we're going to approach this limit on a path that's along the x-axis, and that path is going to be when y is equal to 0. So that's the first step, y is equal to 0. Now that y is equal to 0, what you're going to do is you're going to literally put 0 in for all those places where you see a y. So this would be 0. And then they have 0 here already. So then 0 over square root of x squared is going to be 0 before you even take the limit. And so this is where the limit idea kind of, this is where the limit ideas from Calc 1 becomes a little bit important for us, is that you have to know when you're still in the limit form and when you're actually taking the limit. So for me, I probably would have inserted another step in here to say the limit as x approaches 0 of 0 is equal to 0. But here they just ask you to put 0 in, and then we get 0. So now, similarly, we're going to approach along the y-axis, and here they don't go walk through the process of approaching through the y-axis. But if you were to approach through the y-axis, you would put let x equal to 0 and then go through the same process, and then you're going to get 0, which is what they say here. Since these two limits are the same, we will examine another approach path. So what they're trying to do here is they're trying to get that idea that if you take the limit from one side and you take the limit from the other side, if they're different, then the limit doesn't exist. If they're the same, then the limit does exist. Okay? Now, unfortunately for 3 dimensions, there's a path along the x and a path along the y, and they're the same, but there's another path that might yield a different answer. And so here's where they start examining this other path. Since these two limits are the same, we'll examine another approach. We'll approach 0 along a curve now, y is equal to x. Y is equal to x squared. So if y is equal to x squared, what we're going to do up here is we're going to put y is equal to x squared. I mean, literally, the translation. So x squared is what we want to put in here. What? Oh. My 3 wasn't working. So it looks like that's an exponent. So it's x to the third. So it's x times x squared. We get x to the third. And then we can factor out an x squared from within the square root. And if we take that out, that's 1x under the square root that was taken out. But after we factored in an x squared, we're going to get 1. So I could connect this to the keyboard here, but I might lose my pen access. So the tricky part about this is that yeah. So let's see. So there's this little thing about the square root of x squared. The square root of x squared. The idea is that if the square root of x squared is, if x is positive, then the square root of x squared is just going to be x. If x is negative, then there's some other stuff that comes out. And so there's a little subtle negative sign over here that makes it a little bit different from the top. Although, as x approaches 0, this is all going to be 0 anyway, so I don't think it'll matter in that sense. So those two things we're asking for the same thing. Here, the limit evaluates as this thing, and we're going to put 0 in. So we're going to put 0 up on top there, divided by 1 plus 0, which is just 1, but there's a plus and minus. In either case, it's going to be equal to 0. So this whole thing should just equal to 0. Since all the paths that we've tried now, they've only tried 3 paths. Well, technically 6, but they've only tried a handful of paths. Realistically, there's an infinite number of ways to get to 0. And realistically, to prove that the limit does exist, we would have to try every single one of those infinite number of ways, which, you know, doesn't work because we don't have an infinite number of amount of time. So the way to prove that something does exist is a lot more complicated, and it requires this subject called analysis, where they do epsilon delta business. Yeah.
What if we solve P as an NP? Or we can do polynomial times problem.
Oh, well, that's polynomials, and like this one doesn't have a polynomial in the bottom already. So
I'm talking big O.
No, that's different. Since all the paths we've tried is equal to 0, it's reasonable to suspect the limit might exist and is equal to 0. So to prove this assertion, we have to use a squeeze theorem. Oh, that's another theorem that you can use, which states that if you have 2 functions, g and h, and your function that you're looking at is always between g and h, and then g has a limit that goes to 0, and h has a limit that goes to 0, then the limit for the middle function is going to get sandwiched in there. So here they come up with some weird way to find the two functions. One of the functions is 0, the other function is square root of x. And it turns out that the limit as x approaches 0 of 0 is, well, it's equal to 0. And the limit as x approaches 0 of the absolute value of x is also equal to 0. Yeah?
How do they come up with those functions for the sweep there?
Yeah, I don't know.
Okay. Honestly, that threw me off.
So that's the tricky part, is that you need some sort of experience and knowledge about coming up with these functions. And I have to say that, you know, that's not going to be our main focus.
Okay.
Unless you're a math major, then this might be a little bit more important. But I'm assuming, how many math majors are in there? All right. Good luck. In these problems, though, the more interesting idea is when the limit does not exist. Showing that the limit exists is kind of difficult, kind of hard, and tricky with the idea of using the squeeze theorem or some other epsilon delta business. But instead of doing that, we're going to, I think, in terms of exploiting some of the topics in the limits section over here, I think it might be better to look at when things don't exist. So we'll do problems of limits where they don't exist, and we'll take a look at that idea of going through different paths. All right, next question has several parts. Oh yeah, okay. So determine the set of points in which the function is continuous. So just like back in pre-calculus when you guys were looking at domains and ranges, the important idea here is to look at when things have fractions, because when they have fractions you can't divide by 0. When things have square roots, because you can't have negative numbers under the square roots. And other restrictions like the ln function, you can't have any negative numbers under the ln. If you have one of those, the tangent function, you can't, the cotangent, there's certain angles for the tangent, the cotangent, cosecant, and secant functions where the function will be undefined. So those are the places that we would worry about in terms of finding domains and ranges. So in this case, we have an ln function. So we have some issue here where we don't want this to be equal to 0, or we don't want it to be negative. So it has to be, this expression that's inside has to be bigger than 0. So it says here, given the function g of xy, it can be thought as a composition of g function and f of x function. So it's a composition of two functions, and the f function is a function of x and y. The g function, if you look at within the g parentheses, there's g of xy as one thing, and there's no other commas there. So we can kind of assume that g is a function of only one variable. And we can assume that g is a function of t. And then t is now this slightly more complicated function. Now, t probably wasn't the best choice because we think of t as a parameter. I probably would have called it z just to be a little bit different. But in any case, we know that this x squared plus y squared is equal to 19. That looks like it's a pretty okay function. It seems like we can put any values of x and y in there, and we won't have any issues. The ln function, however, is an issue because we know that we have to have bigger than or equal to, or bigger? Bigger. So strictly greater than, because we can't have it equal to 0. ln of 0 doesn't exist. So we want to make sure that the values that we put in for the ln is going to be always a positive number. Yeah? No, because then you're going to miss like 0.5 and 0.25. So it gets tricky with that stuff. So now that you know that your domain is bigger than, where our t-values are bigger than 0, what is our t-value? Well, our t-values are exactly these expressions over here. The x squared plus y squared is minus 19. So we want to make sure that if you pretend that this is t, back in here, t is strictly bigger than 0. So we want this thing to be strictly bigger than 0. So this can be rewritten as, well, it's just bring the 19 over to the other side. So it'll be x squared plus y squared, and then bigger than, strictly bigger than 19. And then what we can do is we can try to describe that in the two-dimensional plane. We can describe it in words. I mean, having this for mathematicians would work, and a math person would look at this and say, oh yeah, that's what? What? Feasible. Can you describe this domain that we just found? Oh, that's the end of it. What I was interested in doing is taking a look at this and graphing it and seeing what picture this domain is. And then with the graph in 2 dimensions, we can also take a look at the 3-dimensional graph and confirm that it is in fact the domain. So let me do that real quick just to show you what's happening, what possibly might be happening. So let's first look at the domain. You got x squared plus y squared, what? And then this is strictly bigger than 19. So x squared plus y squared is equal to a number is what? X squared plus y squared is equal to 1 is what? It's a circle, radius 1. X squared plus y squared is equal to 19 is what? If it's equal to. It's a circle of radius, whatever, square root of 19, right? So if it's bigger than 19, what can you say about this?
Kind of like everything. It's like an infinite amount of circles past 19.
Yeah, so every circle past 19, but it's not, no, it's just two-dimensional because the domain is in 2 dimensions. Remember, we're in R2. So not just circles, but everything. I mean, we don't describe circles here. So if I graph this, you'll see that it's actually a shaded region outside of that circle.
It will form a donut if we had something less than it as well, right?
Yeah.
So like it was like greater than 19 but less than 20 or like a
Yeah, it'll form a washer.
Yeah.
In math, they call it an annulus. So, if we actually look at the graph of that 3-dimensional thing that they have, which is z or g of x, y, right? That's the function. We'll call it z is equal to the ln of x squared plus y squared minus 19. We don't see anything. I have to zoom out a little bit. So it's essentially a shape with a hole, and that hole is, well, is this hole.
That's the XY plane basically, right? Obviously.
So this is on the XY plane, and that hole that you're seeing here is exactly this hole, which means it looks like this has this has a possibility. It looks a little rough around the edges over here, but it really, I think it smooths down, and it just has an asymptote at a radius of 19, a circle of radius 19 around there. Yeah, you can think about it as a wormhole. Well, because it's jagged, technically it's not supposed to be jagged. It's supposed to be smooth. Yeah, it's the limitations of the thing. All right. So that's the idea with the continuity that they're asking for. They're essentially going to be asking for domains, and your domain is going to be based on your function, based on what you know about your functions back in pre-calculus with the square roots and ln's and those, and then fractions where you can't have 0 for the denominator. Okay. So that should get you going with your lab. Should be a piece of cake. So it'll be due on Sunday. If you guys have your computers, you guys are probably doing it now, right? So let's talk about the rest of the section. And the interesting parts of the section that I was interested in talking about was, I don't have any examples. Bummer. I have to make. So I've noticed that starting from Calc 2, when you're doing integrals, and then going on to Calc 3 stuff, it's always dangerous to make up examples. Because the examples in the book that you see, they're usually nice and worked out, and then you know that there's going to be a happy ending. But if I make it up, you know, it's like integrating something, make it up, and then all of a sudden you can't integrate it, and then you're screwed.
You don't know what's going to happen. You just want to know.
All right, then. Let's do it. All right. So like I said, the more interesting problems are when the limit does not exist. So I want to see if I can come up with an example where a limit does not exist. Make it up. Uh-oh. Hope it works out. Oh, you guys know about the continuities for Calc 1, right? Well, that's for differentiation, just talking about continuity. So let's discuss this real quick. When we take the limit as x approaches a particular value of function, there's a couple of ways for this to not be continuous, and one of the things that we're going to be interested in showing where it's not continuous would be if you know, one of these is an open circle. The other one can be open or can be closed, it doesn't matter. But the point is that if you take the limit as x approaches a from one side, and then you take the limit as x approaches a from the other side, and then these two don't equal each other, then the limit doesn't exist. If they're equal to each other, then the limit exists. But the nice thing about this scenario is that there's only two ways to get to A. Coming from the left side or coming from the right side. And then that's fine. So everything's going to work out okay. But if you have a function of two variables, then your domain is a whole R2 or a piece of R2, but your domain is two-dimensional. And finding the limits as it approaches a particular value. So if you look at this, let's see if we can trim our view here and just focus on the domain. The domain for these old functions back in pre-calculus is really just a number line. And it's a one-dimensional number line. And so like I was saying, there's only two possible ways to get to a value in your one-dimensional number line. So that's how they establish those limits coming from the left and coming from the right side. So now let's take it up to the next dimension. And if you have a function that takes in two variables, so like z is equal to f of xy, we can imagine or picture how this graph might look like. But whenever we're taking a limit, we're going to be approaching not just a value, but an actual point, a, b. And what we could do is that if we look at this from the top view and just focus on the domain, like we did the other one, we can do that. We can play that same game where we're going to follow a path going towards this point. And in the case of one dimension, it was easy because there's only two ways to get there. It actually turns out to be the same path, but there's only two ways to get there, one from the left and one from the right. In 3 dimensions, our domain is in 2D, and the way to get to this point AB can be horizontally from the left and from the right, vertically from the top and from the bottom, diagonally from any sort of diagonal line you can think of. But not only that, you can also approach this path through a curve like y is equal to x squared like they did, through a spiral like this particular drawing, through any other weird function that you can think of that would eventually approach A and B. And the point is that regardless of what curve you approach with, it has to be the same value. Now that's an easy concept idea, but practically speaking, there's an infinite number of paths to get there. So to prove that the limit does exist is a little bit more difficult. But if you can find two different paths that give different limits, then you're in this scenario where two paths give different limits, so the limit cannot exist. And that's what we're going to show, or that's what we're going to focus on, is we're going to come up with some examples of where paths don't exist, and we're going to show that by choosing the right path to get there, we can show that the limit in fact doesn't exist. So let's do an example. This is where I come up with an example. I can't do it. No. All right, what if I all right, let's see if this works. I don't know. Let me graph it first. I'm a little worried. My palms are sweaty, knees weak, arms are heavy. Got vomit on my sweater. Mom's spaghetti. That looks pretty weird. That certainly looked like the limit doesn't exist there. This isn't what I want, though. What?
X minus y to the third over x squared plus y squared.
X minus y to the third.
Would that be nasty?
Oh, this is a good one. Yeah, thank you. What? Oh. Oh, we want it to the second. All right. So here's the plan. The plan is to take paths to get to the zero. Oh, by the way, this is what we're looking for. We're looking for the limit as the pair of points x, y approaches 0, 0 of this function. And what we're going to do, or our approach, is to, let's see, we can have our little map over here and note that this is where we want to get at. And what we're going to do is we're going to try paths to get to the 0, 0. And we're going to designate those paths with an actual XY relationship equation. So like we saw in that example, if we're looking at the x-axis, that's essentially y is equal to 0. So that y is equal to 0 path will cover these two paths going from the left and from the right. So that's what we'll try. We'll try to path y is equal to 0. So in doing so, what we're going to do is we're essentially going to plug in y is equal to 0 before we take the limit. So when we put y is equal to 0 in, so we're going to say limit as x, y. Well, y is going to be equal to 0. So really, in writing this limit over here, we can really rewrite this as x approaches 0 only, since we know that y is going to be equal to 0. But I'll write it like this for now, and then in the next limit thing, I'll put y, just x. Or maybe I'll put it down now. You could just say x approaches 0. That's what's happening here. Now, for the function itself, we have x is x. We don't know anything about that yet. Y is equal to 0. And then here, x is x, and y is equal to 0. And then we'll see that this is essentially the limit as x approaches 0 of x squared over x squared. Now, before we plug 0 in, we would continue to simplify this. And in continuing to simplify, I haven't plugged in 0 yet. And so we simplify x squared over x squared, that's just equal to 1, and so your limit is going to be equal to 1. So what that's saying is that if you're coming from this side over there, you're actually at height equal to 1. So you can think about it as a bunch of friends climbing a mountain, and this is your mountain over here. Should have started with this analogy. You got a mountain in the shape of this function, and then you have a map, and you say, okay, I'll meet you at 0, 0. You have one friend over here and another friend over here, and if they walk through that straight line to get to 0, 0, they're going to get to the same place. Okay? So let's find some other friends. Maybe you have other friends on a different part of the map that will walk towards 0, 0. So this time, the map that we're looking at, the path that we're looking at is a path along the y-axis, so that's the path x is equal to 0. So if we take the path where x is equal to 0, take the limit as x, y. Well, actually, x is equal to 0, so I can replace the x with 0 already. So this is essentially the limit as y is equal to 0 of x. Well, no, x is equal to 0 minus y squared. Oh, x is equal to 0 plus y squared. So limit as x approaches, well, no, this is limit as y approaches 0, right? Because x is already 0. Let's see, this is negative y squared over y squared. Negative y squared is actually positive y squared, right? Negative times a negative is positive, so it looks like this is also going to be equal to 1. So that means your friends that are north and south of your meeting point will still meet at the y level 1 or the z level 1, the height 1. I don't think that's what I saw in the graph.
Yeah. So that's not a great example.
All right. Well, let's take another path. So suppose you have other friends out here that would like to take the path. What's this diagonal path? What? So what if you had another friend who wants to take the path y is equal to x? So let's see, this is weird. Should I put x equals y or y equals x? Y equals x, then I have to change all the y's into x's or x's into y's? Doesn't matter. So I'm going to change everything into x's or y's. What? Change my y's into x's. So I got x and then I see that you're going to be a math major. So since both x and y are the same, we could just, and we change everything into x's, then really this is an x going to 0 business. And if we take a look at this, limit as x approaches 0, x minus x in the numerator is what we have, right? So that's equal to 0. And x plus x squared plus x squared is 2x squared. So yeah, before we even take the limit, and I'll rewrite this limit here to say we haven't taken the limit yet, but before we even take the limit, this whole thing's already equal to 0. So this whole thing's equal to 0. Yeah?
Integrate it, would it be 0 plus c, or would it still remain 0?
We won't integrate this. We're going to integrate functions of several variables. We have 2 variables here. That's why it's a little tricky. So x and y. And so when we do have functions of several variables like this, we're going to have to learn a different kind of integration. Going to have to integrate twice. All right. So what we're saying here is that your friends coming from north, south, east, west will be going to the meeting point, and they would be at height 1. And then your other friends that are going from northeast and southwest, northwest and southeast, whatever, coming from the diagonal, they will end up being at height 0. So what we've shown here is that we have, I can pick either of these two, but I'll circle this and say that these two are not equal. And so we have that scenario like in Calc 1 where we come from one side and come from another side, and then we have 2 different limits. So we have to conclude at this point that the limit does not exist. So that's how we would show the limit doesn't exist in these types of scenarios, is that if we can find 2 paths that get to this at the 2 different heights, then your limit won't exist. So we could see a 2-dimensional picture. Let's try to look at the 3-dimensional picture again. And you'll see what's distinctive about this particular graph. Maybe choose a color. I'm waiting for my x to come around. So this is my x-axis. I will stop it when it's right about there. And this is supposed to be smooth. It gets jaggedy because of the finite rendering that the computers have. But let's take a look at this graph and analyze it a little bit and draw on it and stuff. So what we're saying here is that for your friends that are coming along the x-axis, was that what was first? Coming along the x-axis, they might start off down here kind of low, but then they'll eventually come up here to the x-axis. And then same thing from the back side. They're going to come up here and have a height of 1. And coming from the y-axis, they'll also be climbing this hill and eventually get up here at a height of 1. Now, for those people that are coming from the northwest position, when they walk along 0, 0, they're going to end up down here. So that's the discrepancy. I mean, it's a lot more complicated than, back in Calc 2 or Calc 1. It's a little bit more complicated than, coming from one side and right side and left side, and then you get 2 different values. Here, you're coming from multiple paths, and you have to find 2 paths that don't equal each other to show that the limit doesn't exist. Yeah?
How do you know what path to choose?
How do you know what path to choose? That's where you practice and practice and practice. Yeah. So the usual paths to try are the paths that we tried. The y is equal to 0, x is equal to 0 path. And then the third path to try is this. Beyond that, you have to try to look at the graph and try to imagine what can you replace x with or what can you replace y with that would make this not equal to the rest of the things that we've found. Say it again? Oh, negative x doesn't equal a 1? It's equal to 0, huh? Oh, I think it's equal. Oh, yeah. So that's yeah. Is equal to what? 2. So that's even worse because now not that it's worse, but I mean, it's not 1, right? As long as it's anything else, then it would be not continue or not. The limit doesn't exist, and that's what we're curious about.
I guess the graph will connect that one at height 1, but then it will like below it will make a whole kind of
Yeah.
So those top so like at 1, that's where it's connected.
Yeah, this is all connected here. This should all be part of the graph. Now there's a couple of other examples that I was looking at that, like the one to the third power. Let's take a look at the graph of that. So this thing, I think if I look at it carefully, there's a little kink there, right? But I still think that the limit will exist because it looks like regardless of what path I take going to 0, 0, which is usually the issue, it looks like I'm still going to be at 0. So now, it's a little kink in the hole. So I think regardless of what path I take here, it's going to be equal to 0. So we won't be able to prove that the limit doesn't exist. So the opposite side is to try to prove that the limit does exist, and that's going to require your squeeze theorem or something else. And I guess physically, what the way to try to describe this, and I don't know if this will make sense to you, but somebody described it to me this way. If you have a piece of paper, right, and if you can do any folds that you might come up with where you can still make it look like this graph from a piece of paper, or even like a rubber, those flat rubber things that you can stretch out and stuff. If you could stretch these things out and mold it a certain way and still make it look like your graph, then the limit is still going to exist. Now let's take a look at that one that doesn't exist again. And here, in this particular scenario, there's no way to fold the paper, or there's no way to mold that rubber sheet and make it look anything like this without having to cut it up. And like I said, this should be smooth up on top and smooth down here below, so it looks like it's going to...
So if you did even power,
No, this one looks like it's still going to exist there.
Oh, okay.
I think it's just that 2.
Yeah.
That's the big issue. Okay. So the other bullet point in my agenda is looking at limits for 3-dimensional functions. And I don't know if I want to do that. It's kind of complicated. What? What? Yeah, just think about it over the weekend. All right, so I will have this lab, the one that we just did, and then the next lab, and maybe even a third lab due on Sunday night. Today or tomorrow? I suppose I could change it now. I have 5 minutes since you guys are all going to leave. All right, see you guys on Monday.